Welcome back. Now that we learned about the concept of estimators and we know how to apply the mean and covariance propagation laws, let's look at some of the properties of estimators and see in particular what are the properties of the weighted least squares estimator. To start, I want to point out the difference between two different kinds of estimators, linear versus nonlinear estimators. We saw that in general case, an estimator is a function of the random variable y. If this function is linear, then we can write it as a multiplication of a matrix, let's say matrix L, to the observable vector y. In this case, the estimator is a linear estimator. For example, let's look at the weighted least squares estimator. In this case, the weighted least squares estimator x hat is the multiplication of this matrix, I denoted it by L, with the vector y. So the weighted least squares estimator is a linear estimator. Now, what can we say about the statistical properties of linear estimators? In our mathematical model, with the functional model as the expectation of y being equal to ax, and the stochastic model as the dispersion of y being equal to covariance matrix of y, if we know that observables are normally distributed, what can we say about the distribution of the least squares estimator x hat? From statistics, we know an important property of linear functions, which is that a linear function of normally distributed random variables is again normally distributed. Therefore, as a weighted least squares is a linear estimator, we can say that if the observables are normally distributed, the estimator x hat will also be normally distributed. Okay, now what can we say about other statistical properties of x hat? For example, what is the mean or expectation of x hat? If x hat is a linear estimator, hence x hat equals Ly, we know that its expectation can be written as L multiplied by the expectation of y. In the case of weighted least squares, for example, the expectation of the estimator can be written as the multiplication of this matrix to the expectation of y. From the functional model, we have the expectation of y equals ax. Inserting this equation here, we can see that these two terms cancel out each other, and finally, the expectation of x hat is equal to x, or equal to the true value, the unknown true value. Even though the true value of x always remains unknown, this expectation equals x is an important result. It means that on average, if we have a large number of realizations of x hat, we expect the mean value of realizations to converge to the true value of x. We can also reformulate this and say that the expectation of x hat minus x is 0. It means that the mean of the estimation error is 0. Which is indeed a desirable property. This property of the expectation of x hat being equal to the true value is called the unbiasedness property. That is, our estimator is unbiased and statistically its mean is equal to the true value. Well, so far so good. In this lecture, we learned that with our mathematical model, with normally distributed observables, the weighted least squares estimator is a linear unbiased estimator, which itself has a normal distribution with mean equal to the true value. We can also ask now what would be the dispersion of our estimator, or the covariance matrix of x hat. Note that Qx hat describes the precision of the estimator. The detailed derivation and interpretation of Qx hat and the quality of the estimators is the topic of the next unit. But here, I just want to conclude this lecture by saying that in general, with estimators being random variables, we are ideally interested in an estimator with possibly the lowest dispersion in Qx hat, or in other words, in the most precise estimator. Let's see in the next section how we can find such an estimator.